2, 1. All right, so derivatives continued, some applications. The unfortunate part, I guess, for students who are doing calculus and you're going to get into some derivative applications is going to be the fact that you may not have the breadth of kind of knowledge and exposure to many of the sciences. And one of them, which calculus likes to borrow from, is definitely physics. So here's an example with regards to kinetic and potential energy. For those students who have done physics, they'll be kind of familiar with these formulas. But those who haven't kind of have to grind away and be able to understand, okay, how to utilize those equations and then formulas to find out whatever derivatives you might be working with. Now, the nice thing is, to be honest with you, the equations and functions you're going to be working with are not going to be that difficult. So here, I'm not going to make the assumption that you have taken physics or something of that nature, but I will make the assumption that you're comfortable with functions. So here you have two functions within here. So here's a function ek, and it's going to be dependent on time. I'm going to just show that to you in just a moment. I dropped the t for the time being. This equation is for kinetic energy, and kinetic energy just means energy when you are moving. So in terms of motion, I'm not going to go any further than that. And it is equal to 1/2 mass. So that's the m, it stands for mass of the object that's moving, and multiplied by its velocity squared. So that's the kinetic energy. All right, so within here, we're going to have this velocity that's going to play a role for us. The mass is constant of whatever it is that you are working with. Now, the units, there are many units for energy, but typically the unit that is used is the standard unit, and that will be in joules. The second equation here is the energy or potential energy with regards to gravity. So sometimes we call it gravitational potential energy. That's why you have a G and a P there as a subscript. At least that's what I like to use. And it is the energy that you have with regards to how far you are away from a particular surface. So it's always relative to a surface. Now, that energy is equal to mass of that object, okay, that you have, multiplied by g, which is the acceleration due to gravity, which is going to be 9.8 meters per second squared, and then the height that it is, okay, or the distance that it is away from the actual surface, okay, or the ground. And the unit also is joules. So those are the two kind of equations that we're going to be using and the formulas that we're going to be using. Now, I have this example right here, which is an example that I did when we were discussing derivatives with regards to kind of position, velocities, and acceleration. So I'll put up a link up above there to this exact concept. Okay, so you can go back there. And within here, so what we have is we have somebody, so maybe me, okay, and I'm throwing up a ball. Now I'm going to give this ball a mass. So this ball is going to have a mass of 300 grams or 0.3 kilograms. That's what we're going to use. So kilogram is actually the metric standard within here in our calculations. The g, so notice the g is the acceleration due to gravity. So it is an acceleration, which is 9.8 meters per second squared. So I'm giving that to you. And I'm throwing up this ball at an initial speed. And this initial speed, so it's basically I'm throwing it upwards at 10 meters per second. And now the position, so the actual position, so notice I use S, okay, or kind of the displacement within, is with respect to the ground. So I am 50 meters above the surface. I am throwing it up at 10 meters per second. So the ball's going to go up. Gravity is acting on it. So it's going to slow down. And then eventually it's going to fall back down. And that is my equation for the position that I am, okay, relative to the ground. And of course, if it, we're going to do it from, time 0 all the way until it hits the ground. We can't really go and bypass the ground. Now, this is a quadratic. So this particular equation, if we would graph it, it's going to be like a quadratic. So it's going to start off, okay, at t is equal to 0, it's going to start off at 50, and then it's going to kind of go upwards, okay, and then eventually it's going to start coming down. And as it comes down, as gravity is acting on it, it's going to go faster and faster until eventually it hits the ground. So now with this information, what we want to be able to do is we want to be able to do the following. We want to be able to plot, okay, our kinetic energy. We want to be able to plot our gravitational potential energy. So let's do those two. And notice that I am, okay, so my independent variable is going to be time. Now, why is it time? Well, so within here, okay, so notice within, I have my velocity or my speed that I am moving at, so either up or down. Okay, so initially it's at 10 meters per second, but it changes, right, because of gravity. So what I will do is, so within here, I can get what my speed is, and that is nothing else but the derivative of the position, okay, within here. So if I do that, this is just simply going to be 10, and then minus 9.8 t. Okay, so if I take the derivative of that s function in there, so that's my velocity. Now that I have it, I can substitute it into here, and I'm going to get what my kinetic energy is. So here, let me just kind of go down. So my kinetic energy, so my function is going to be, so this is 1/2, okay, times mass. My mass is 0.3 kilograms. And then my velocity is 10 minus 9.8 t, and this is supposed to be squared. So that is my kinetic energy. So notice it is also a quadratic function. Now my gravitational potential energy, I can do exactly the same thing. So I will have my gravitational potential energy with respect to t is going to be my mass, which is 0.3, multiplied by my gravity, which is 9.8. Okay, so that's coming down right there, and then multiplied by the height. But the height that I am at is nothing else but the position, right? So it is the position of the ball, that's the height that I am at. So that is going to be 50 plus, okay, so 50 plus 10t minus 4.9 t squared. All right, so that is that. Now, by the way, this gravity we could get, because this is nothing else but just kind of the absolute value of the second derivative, right? Because this is the acceleration that we are experiencing, but because we've made the acceleration, so we made down to be negative, right? So if you would take the second derivative of s, you're going to get negative 9.8, which just simply means that it's falling down, and we want to know its magnitude, which is 9.8 in here. And if you would substitute that in, you're going to get your energy, your gravitational potential energy equation. So let's graph these, or let's plot these out. Now I'm going to use decimals, although these are both quadratic, so I can technically utilize the skills that we have by now to be able to plot these, but that's going to typically come in a separate chapter. So for us, what I want to do in here is I want to utilize it using decimals to get a good view, okay, of this. So I'm going to call this E. Okay, let's put a subscript K for kinetic energy. This is with regards to T is equal to, so it's going to be 1/2. I'll just put actually M. I'm going to define M so that I can use 0.3 if I wanted to change. And then this is going to be, so within here, so that's going to be 10 minus 9.8 t, and that's squared. All right, so this is what we have. And so this is for t, so I guess that we are definitely, now I don't know, we're going to hit the ground at some point. So, maybe let's just say that t is greater than 0 for the moment. I'm going to go up there, so obviously we're not going to have an infinite amount of energy in here. So we're going to run out. And in order to do that, let me just plot. So I'm going to just plot st. this is going to be equal to 50 plus 10 t minus 4.9 t squared. All right, and that's going to be, so indeed t, and I guess again, so we need that point 4.375. So that's when it hits the ground, 4.37. Sorry, did I say 5 or 4? Okay, I think it was that. So there we have it. Okay, and then I can do the same thing here in terms of the between 4.374. So that's going to give me the amount of energy I have. That's my position. So notice that's exactly how it looks like, right? The ball goes up. Basically flat lines, okay, so meaning that it stops at a certain point and then it just starts coming down. So the velocity is going to be negative because it's negative, meaning that it's just going down for us in here. So that's my kinetic energy, so that's the red one. Now if I plot, I'm going to call this GP of T, and this one, oh, okay, so great, because now I have mass times, I guess, 9.8 times, I guess, ST. All right, so this is going to give me my potential energy. So notice the potential energy right there. So it starts off, and it makes sense that it's going to get bigger because the height, right? So we initially, as we throw it up, it's going to get higher and higher. So the potential energy, okay, is bigger because it's dependent on H. The mass doesn't change, gravity doesn't change, and the only thing that changes is the height. So that means it goes up and then it comes down. And then eventually as it hits the surface, notice the difference between, so let me just remove this. Okay, so notice that these basically overlap. So the gravitational potential energy and the kinetic energy are different. So kinetic energy is dependent on the movement of this particular ball or the movement of anything. If it doesn't move, if the speed is 0, then kinetic energy is 0, which happens, okay, at the peak there, so at 1.02 seconds. While your potential energy is the highest at that point, so it has the most amount of energy because it is the furthest away from the ground. But then the potential energy starts to dissipate because it gets closer and closer, but your speed, because your gravity is pulling it down, your speed is getting faster and faster. So that's why at the end, as it kind of almost hits the surface there, the ball has the biggest speed, but it has no gravitational potential energy because the height is 0. So that is kind of visualizing what happens in here. Now, with regards to derivatives, so it says, find the derivative of your kinetic energy function and then find the derivative of your gravitational potential energy. I'm looking on the left in part C, and then graph them. So that's not a big problem in here. This is a relatively simple calculation. So we will have, okay, so this is for the kinetic energy. So if we want to find the derivative, so this is going to be the 2 will come into the front, so we'll cancel that half. So that's going to be just 0.3 multiplied by 10 minus 9.8 t, and then so we're using the chain rule in here, so times negative 9.8. So that's what we would have in here. We can certainly multiply all of these, and this is just going to be a line, and that makes sense because it's a quadratic. So that means if you take the derivative of a quadratic, then what you will have is you're just going to have a straight line. So that is that. Now for the gravitational potential energy, okay, so for this one, so that's going to be, I guess, I'm going to leave this 0.3 times 9.8 in front there. And then we're going to have 10, the derivative of that, and then minus, and this is, I guess, 9.8 t. So that's what we will have right there. So that's going to be my derivative of the gravitational potential energy. And so graphing this, yeah, so if I graph this out, okay, so within here, let me maybe remove this. Okay, so we want to graph, so I'm going to call this E, And so within here, so I just want to show you something. So this is going to be the derivative of, I'm going to put a little d in here for the derivative. So you can do that on Desmos by just simply utilizing the prime as so. And that's going to be the prime of, sorry, I'm going to do this. This is of the k, right? And this is going to be prime, if you do that, of t, and that's going to take your derivative of the kinetic function. So this right here, so I'm going to call this kd, like that. Okay, and now just so that, you know, I can prove that to you, so let me call this, you know, ekd2. Okay, and this is the actual derivative that we took. So this is going to be 0.3, which is the mass. So we already know what the mass is, times, so notice negative. Okay, so it's going to be negative 9.8. So that's going to be negative 9.8 times, and then 10 minus 9.8t. Okay, so that's going to be that. And now notice that these two overlap. All right, so this one and this one, they overlap. All right, the only thing is that the derivative is bound between 0 and that 4.374, so the time. So we can also set, okay, this to be between, you know, 0 and that time. So those are the same exact things. And then plotting your other one, so this is going to be the gravitational potential energy. So gravitational potential energy, so the derivative of that, you do have to define it within here. So that's going to be E. Okay, so it's going to be GP T, and then there you go. And notice that they crisscross, right? One has a positive slope going up, one has a negative slope. Okay, they touch base within here. This is 1.02, and that should make sense because at both of those moments the slopes are 0, and this kind of goes back to the original functions. So if I go here and then I plot this, okay, within here, okay, so now notice what happens right there. Okay, so those are the derivatives, and the derivatives are 0 exactly at the peaks, right? So this is what we would have. Now the last part, which is D, what is the rate of change of the kinetic energy at t is equal to 2 seconds? So within here, so what I can do at 2 seconds, I mean, sure, I can substitute it in, use my calculator, but on Desmos, I already have this. So I'm going to do the, I call this KD, right? This is at 2 seconds. That's 28.224 joules, right? And this is joules per second. So what does that mean? So that means at 2 seconds, okay? So let me remove this. I'm going to just hide this away, and this is kinetic energy that they're asking me about. So notice if I'm going to shift this over. So if I go along here, okay, so this is at 2 seconds, so that's right here. So notice that the derivative there is positive, right? So the derivative is positive. The answer we got is 28.224 joules, and it is a derivative, so it's joules per second. And what that means is that the kinetic energy is increasing, right? It has a positive rate of increase, and you can see that indeed. Okay, so that's exactly what's going to be happening in here. Okay, so with this function at that particular point, right? So we know what that derivative is, okay, at that point, so we can have a tangent line and notice that it is in fact increasing. So up to that 1 second, the kinetic energy is dropping, right? So it's decreasing, and that makes sense because the ball is going up, but gravity is acting against it, so it's slowing down, stops, right? So it's 0, so that would have been 0, and then it starts to fall back down and it starts to pick up speed, and that what the derivative would be right there. All right, so that's an example, kind of exposes you to another physics problem So I hope that you found this useful and a nice kind of explanation, and you can apply the derivatives. Taking derivatives is not very difficult. I think the biggest challenge for you will be is to get comfortable with all of these different quantities. So from energies, speeds, velocities, accelerations, and anything else that you might take on. So there's abundance of these that you can run into. Okay, thanks for watching. We'll see you in a future video. Happy calculus studying. Bye, everybody.